All right, we're going to check out the second and third homework assignments for Chapter 6. I'm going to knock both those out here. And then I also posted a key, just a static key, not a video key, for the homework, or not the homework, but the amino acids worksheet that we did on the final day of Chapter 6. So that was October the 6th of last week. I guess that was last Wednesday. We didn't quite get to that amino acid worksheet in class, so I posted a key that Dr. Wysocki had made in a previous year for that on Canvas, and her explanations on there are pretty detailed on the front page, which we didn't get to. The back page we actually talked about in class a little bit, so make sure you go over that because all that amino acid stuff is fair game on the exam. Okay, now let's look at our homework. So this is homework 2. This is chapter 6 homework 2 we're starting with. Okay, first one asks us if we have this molecule and it has a pKa of 4.6. The question says, at what pH would you expect mostly the uncharged form? At what pH would you expect mostly the charged form? So this is talking about the pKa of this acidic proton. So this becoming like an NH2, right? It's talking about like this reaction. Uh-oh, dot cam's gonna fall. Talking about this reaction of this thing becoming neutral, right? Plus an H plus, or technically plus H3O plus. Technically, we're talking about the reaction with water when we're defining this pKa, but you know, this is the important proton transfer step that we're thinking about here, or that we should be thinking about here. So we want to know, where are we going to have mostly the uncharged form? Where are we going to have mostly the charged form? So we know when the pH equals the pKa, then we would have 50% of the plus and 50% neutral. Okay, or HA plus and 50% of the just neutral A, which in this case is our conjugate acid, right? So this would be like my A, this would be my HA plus. When the pH equals the pKa, I have half of one and half of the other, right? They're present in equal amounts. So if I go more acidic, so if my pH is less than my pKa, then I'm going to have more of the acid form, so HA plus in this case. If my pH becomes more basic than my pKa, so my pH is going to more basic pHs or greater pH than the pKa, then I have more of the neutral form. Okay, so at a pH below 4.6, I'm going to be jamming protons onto this to force it all to be this side. If I go to a pH above 4.6, that means I'm taking protons away, so I'm going to be more on this side. Okay, you don't have to do any calculations. Like I think the book had calculated where you had 99% of one and 1% of the other, something like that. You know, we just want to know where's the majority. To me, the majority just means anything over 50%. It didn't ask you for a super majority of the conjugate acid or anything. Okay. Now, 45, question 45 wants to know, can we use these different, stupid cam, can we use these different reagents with ethanol? So here's ethanol, right? CH3CH2OH. So in order to think about, can I use all these different bases with ethanol, I need to think about, what is this question really asking? It's asking, if I want to use this base, if I put it in ethanol to dissolve it, is it going to just react with the ethanol before it actually reacts with whatever acid I'm interested in actually doing chemistry with? So I need to know, how acidic is this H? And the answer is it's an alcohol, so we know it's around 16. Okay. So then I just need to figure out what are my pKa's of the conjugate acids of all these bases, and go from there. Okay. So this one, the pKa is like 38, right? Which means that this going to NH3, okay, the reverse reaction of that is 38, right? Really, I guess we wanted to draw this backwards. 38 is our pKa. We need to draw the double arrow. So, you know, perhaps the best way to think about these is to actually fully write out the reaction of like CH3CH2OH plus NH2 minus is going to go to CH3CH2O minus plus NH3, and then write out your appropriate pKa's for each of these. So this one's 38, this one's 16, and I know my reaction is going to favor the side with the larger pKa, right? I could actually calculate the KEQ for this reaction. It'd be 10 to the 38 minus 16, so 10 to the 22nd. Or I can just look at this and say it's going to go to the side that's the more stable, the weaker acid, the more stable molecule, which would be this. Okay, so in this case, it's going to go towards products, which means this is going to react with my ethanol. That's not what I want to happen. I want my ethanol to just be a solvent and just be there to dissolve everybody and not actually react with anybody, because I want my things to react with each other and not the solvent. Okay, so in this case, no, we can't use NH2 because it's going to react with our solvent. Okay, this guy is going to react with our solvent. Okay, that's what I'm trying to say. We don't want that. Looking at this one, I need to think about what's the pKa of my conjugate acid. So this carboxylic acid pKa is going to be about 5, like 4 to 5 for this molecule. I think acetic acid is the one that's in the book. It's like 4.75. So again, I'm thinking about which one's going to be favored. I want my solvent to be favored. I don't want my solvent to react, right? In this case, this was favored over the solvent, so my solvent reacted to form this. In this case, this is the weaker acid, right? My pKa says that this is the more stable acid than this one. So it's gonna stay on this side, right? It's gonna go towards the larger pKa value. And I could write up the full reaction if I wanted to. Or I can just think about the pKa's that are relevant and say, yes, this is gonna work. Okay, this one, the conjugate acid is HCl. The pKa of HCl, we don't even know its exact value, but it's negative something. Okay, I'm just gonna say pKa is less than 0. And we know our pKa for this is 16, so this one's also going to be fine. The reaction is going to favor the side with our solvent on it and not the side with HCl. Okay, next one. This one is not a pKa that you had to memorize, but you could have looked it up in your textbook. The pKa for a phenol is about 10. Okay, so again, we're favoring the larger pKa. We're going to favor our solvent, so that's fine. We want our solvent to stick around. We don't want our solvent to react. So we always want our solvent pKa value to be favored. Okay, HCN is our conjugate acid here, which this is a C triple bond N. So this is going to be a similar pKa to what we would expect for an alkyne. I think it's actually a little bit more acidic than that even because the N is so electronegative. Is this one in our pKa table? Let me look. I don't know the pKa of this one off the top of my head, but I would guess it's probably like 20 or so, something. Yeah, I don't see it in the table. So we could approximate this as being kind of like an alkyne and call this pK about 25, in which case it would be fine. Okay. Or no, it wouldn't. Not if its pK was 25. Let's actually look up and see what the pKa of HCN is, because we would need to know that and we don't need to memorize that. Okay, so HCN pKa is considerably lower because of the nitrogen. It's actually 9.2. Again, not a pKa value you'd have to memorize. But this question was being asked assuming that you could look at the pKa tables. Okay, so HCN pKa is about 9.2. That means the ethanol is again going to be more favored. So, so yes, we could use this. Okay, we need to know that pKa for that though. Then this last one, so this is propane, right? The propane ion. It's propane anion. So this is going to be like an alkane pKa, which we said are about 50. Okay, so in this case, we're checking out the pKa of this molecule, right? This is my conjugate acid. This is going to be a lot more stable than this is, okay? Because this says my pKa is 50. This is my acid here, right? We're looking at this reaction. If my pKa is 50, that's saying this going to this, the reaction constant for that, or the rate constant, not the rate constant, the equilibrium constant is like 10 to the minus 50. Okay, so again, if I were to set up my entire reaction with this, I'm going to see that this side is going to be favored with my conjugate acid that has a high pK value of 50. So this one would not work with ethanol. Couldn't use that one with ethanol. Okay, next one, which is number 47, says draw the products of this reaction. So we're basically just pulling off this proton from this alkyne to make this acetylide ion and NH3 neutral. And then it says draw a free energy diagram, indicate whether it's endothermic or exothermic. So pKa for an alkyne is about 25. pKa for this going over to here, right, at NH3 going to NH2, that pKa is about 38, which means we're going to be favored, right? Our equilibrium constant's approximately going to be 10 to the 13 going to the right, okay? So the right side should be favored, which means it should be lower in energy. So this would be my reaction diagram, something like that. Okay. 49 is the last one, and I believe that one we're just going to look in the book for. So let me get the book. Okay, so 49, it wants us to know, it wants us to say, if we have these two separate reactions, which product is favored in each of these reactions, looking at these diagrams. The most favorable product, or the product we're going to see in the greatest proportion at equilibrium, is the most stable one, right? Things always want to react in a way that makes them more stable. So the one we would expect more of in the left reaction would be Y, right? Because this one's Y is more stable than X, so we should expect to see a larger thermodynamic proportion of Y. On the right side, Y is also lower energy than X, so Y should be favored by this reaction as well, right? It favors the one that's more stable, the more stable product. These lines only have to do with the activation energy, which only tells you something about the rate and not the equilibrium position. Okay, so in both cases, Y is more stable, so Y is going to be more abundant at equilibrium. Okay, hopefully that transition wasn't super jarring because I didn't tell you I was switching off the book, but we're now looking at homework 3 for chapter 6. We're doing these all in one big key. Okay, so now this is chapter 6, homework 3. Number 59 says what? It says the pKa of these are 9.1, 9.2, and 9.0. Match the pKa with the structure. Really all this is asking is which one of these is most acidic, which one is the least acidic. Well, remember if we think about the conjugate base, let me just draw the general structure of the conjugate base down here. We have an O minus, and then we have a halogen in this position. A lot of times the halogens we like to abbreviate with just X. So a halogen in this position. We want to think about which halogen stabilizes this negative charge the best. Okay, so in this case, the charge is not actually on my halogen ion, or excuse me, my halogen atom. My charge is not actually on my halogen. So I'm not thinking about the size of the halogen for this question. I'm thinking about the electronegativity of the halogen, right? The more electronegative it is, the more it's going to withdraw this charge and sort of delocalize it and help it become more stable. So chlorine is the most electron withdrawing, right? It's the closest to fluorine. Bromine is the second most, and iodine is the least. So this one should be the most acidic. If I'm looking at the charge actually on the chlorine and the iodine, this would flip. Okay, but the charge is on the oxygen. I'm just looking at their electron withdrawing ability. This one would be the most acidic. This one would be the least acidic. Now, how does that fit with my pKa's? Well, the lower the pKa is, the more acidic it is. So the chlorine should be 9, this one should be 9.1, and this one should be 9.2. Okay, so again, size versus electronegativity. The size is more important when that's the actual atom bearing the charge. In this case, it's not. All right, 62 says rank these from weakest base to strongest base. So I'm going to say down here, strongest equals 1, and my weakest I'm going to label with a 7. Okay, so strongest will have a 1, weakest will have a 7. Okay, now remember, when we're making an apples to apples comparison, we're looking at two very similar looking molecules or functional groups or protons, I guess, specifically acid-base sites in a molecule. This is where we use Cari. Okay, so the first thing we need to look at is charge. I'm only looking at the charge on sites that are comparable to each other, right? If you think about the quiz we just had, we saw with an amino acid, the NH3, or I guess it's RNH3 plus, the amine side that's protonated, has a positive charge, is less acidic than the neutral carboxylic acid. Okay, so when we talked about this in class, because I think a lot of people were confused about this after the quiz, this is only for sort of tie breaking. Okay, it doesn't mean that a positive charged acid is always a stronger acid than a neutral acid, right? Because if you think about sulfuric acid as a good sort of benchmark, sulfuric acid is a neutral acid, okay? And the pKa of this is what? negative something. It's like -9. I don't know. I'm just gonna say the pK is less than 0. The pK of this thing is like super, super. It's a really strong acid. Then we have things like NH4 plus, where we know the pK of this is like 9.4. Okay, the pK is about, let's just call it about 9. This is a positively charged nitrogen. Okay, but it's a much weaker acid than this. So the charge is we're only talking about the charge considering the charge in tie breaking two similar molecules or similar sites in a molecule. Okay. If you're confused about that, then ask about it during the review session, or come talk to me about it, or email me, or something. Okay, so charge. So strongest base. Uh, it's kind of like how we said if we're doing an apples to apples comparison, a positively charged species is going to be a stronger acid. A negatively charged species is going to be a stronger base than a neutral species. Okay, so looking at all of these things, we only have one that's neutral. This thing, I don't know where you're going to put a proton on this. I guess you could put it on one of these lone pairs on the oxygens, on either of these oxygens, but good luck doing that. Okay, it's going to be very extremely weak. So this is going to be my weakest. All right, this is going to be number 7. And I'll just kind of circle each one when I'm done so I know not to revisit them. This is going to be the weakest. Okay, now so that was charge. So charge is done. Okay, now compare the atoms. So I have carbon, oxygen, carbon, oxygen, carbon, carbon. I know my negative charge is more stable when it's on oxygen. So I'm going to have stronger bases when I'm on a carbon, right? But since I already did this one as the weakest base, let's go through and find all the, the next most weakest base, I guess. Which one of these, a question I guess that we're asking ourselves is, which one of these is the most stable? And I'm only going to look at the ones with oxygens. So this one versus this one. They look almost identical, except this has 2 fluorines. And we know fluorines are electron withdrawing, which are going to make this more stable. The more stable this is, the less likely it's going to be to stick a proton on there, to pick up a proton. So this one would be 6 then, and this one would be 5. This one's the next most stable. Okay, so this one and this one. All right, next one. We have carbons. Carbon, 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 and carbon. Right? If we think about resonance, how far can that get us? I'm thinking resonance can take us pretty far. So let's compare resonance, right? We're looking now at resonance. We already went through our atoms, okay, of our overall group here. So let's look at resonance now. So among these, how does resonance play a role? This one, we have a resonance structure where we can put the negative charge on this oxygen, right? I can make a double bond here and pop this up onto this oxygen, this lone pair. So I have one oxygen with a minus charge here, oxygen with a minus charge here. So this has 2 good resonance structures. This one has 1 good resonance structure where I do that same thing and make a double bond, negative charge on oxygen. Double bond, negative charge on oxygen. I can do that on all of them, right? Double bond here, negative charge would then jump up to the nitrogen, not the oxygen, but it would still at least be off the carbon. So since this one has 2 good resonance structures, we said this has 1, 1, and 1. This one's going to be stabilized a lot by those 2 resonance structures. So this would be the next weakest base, or the next strongest base, I guess, since we're increasing our basicity as we go through our rankings. Then we have to think about these 3. We said they all have 1 good resonance structure, right? Or 1 better resonance structure where we make a double bond and move the negative charge up to the heteroatom, the one that's not carbon. In this one, we end up with a negative charge on our nitrogen, which is going to be less stable than a negative charge on our oxygens. Okay, so now we're kind of going within this subgroup of resonance rankings. We're going back to an atom argument. Okay, so you go through these kind of multiple times when you're doing this ranking. Basically, you have to use these to split your molecules into subgroups, and then use these to rank the molecules within those subgroups. So again, this one doesn't stabilize the negative charge all that much. So this is probably going to be my strongest acid then, because these other 2, I'm just trying to figure out, which one of these is less stable between these 2, because I know they're both going to be more stable than this one with the negative charge resonance onto the nitrogen. Okay, so these both have that same resonance form where we move the charge up to the this other O, right? Double bond, charge goes up to the O. So that gets resonance is the same on these two. I need to look at inductive effect to separate these last two. This one has an extra methyl group. Okay, so electron donating group is going to destabilize that negative charge. So this one's going to be more basic than this one is. Okay, because it has that extra methyl that's donating, that's not going to make that negative charge as happy. Another thing is we know carbocations, the more substituted they are, the more stable they are. Carbanions is the opposite. The lone pair needs extra room to breathe. So a carbanion is more stable the less substituted it is. And I believe radicals follow that same argument too. Okay, 64, I have book written here, which means we're going to look at the book. So let me transition to the book. Okay, here we're trying to rank the stronger base. Okay, so this one versus this one. Well, we just said earlier, if we have a negative charge, that's generally going to be a stronger base than an uncharged if we're looking at apples to apples comparison here. So this one's a stronger base of this pair. Down here, same idea. The positively charged one is going to be the weaker base, right? This one has already accepted an extra proton that it didn't want to make it positively charged. This one has two lone pairs I can stick a proton on. This one only has one. And if I stick a proton on here, it's going to make this a +2. So that's going to be even harder to, increase the charge on that oxygen because oxygen doesn't like having a positive charge. So this one is going to be the stronger base. You can also think about the conjugate acids. This conjugate acid is going to be a plus charge. This conjugate acid would have a +2 charge, which would make it a stronger acid, which means this is a weaker base. Okay, this one is just pKa, or you can think about the hybridization. We know the pKa of an alkyne is like 25, and the pKa of an alkene is like 44. So alkene is going to the alkenyl or the deprotonated alkene is going to be the stronger base. Okay. We also know that sp carbons are more acidic, right? If I have a sp hydrogen, it's going to be more acidic. So the conjugate acid of this is stronger than the conjugate acid of this, which means this is a stronger base. Here we're just looking at conjugates again. So if I stick an H on here, I get an O with a plus charge. If I stick an H plus on here, I get an N with a positive charge. Since O is more electronegative, that's less stable. So this is my better base. pKa argument, this is like a ether pKa, which is probably somewhere in the neighborhood by an alcohol versus an amine pKa, right? So this one's like 9. This one's probably more like 13 to 16 for an ether. But anyway, we can just think about the conjugate argument. That works too. Here, N versus P, N and P are in the same column. So thinking about size, P is larger, so it's better at stabilizing the negative charge. More stable negative charge means a weaker base, so this one's the stronger base. These two, this one has a lot of resonance stabilization. This is a cyclopentadienyl ion that we talked about in 241. This negative charge can actually resonate on every single carbon, so it's spread out among all 5 carbons here. This one has no resonance. So this is more stable. This is a stronger base. Okay, looking at these two, this one's stabilized by resonance. I just said that. This one's stabilized by the inductive effect. But remember, Cari, C-A-R-I, says resonance is more important. Okay, so the resonance stabilizes this more than the fluorine stabilizes this. Since this is less stable, this is my stronger base. Down here, they both have equivalent resonance. They're both going to be able to spread this negative around all 5 carbons because this one is just all the H's have been replaced with F's. So resonance is equal. This one has better induction stabilization because of the electronegative fluorines. So this is more stable. This is the stronger base. And then here, I said this one has resonance around all 5 carbons. This one only has resonance to move this negative charge onto 3 of the carbons. It can't actually spread it all the way around the ring. So this one is less stabilized by resonance. This is my stronger base. Here's what those resonance structures look like, in case you're curious. Okay, so pause the video here and analyze these if you would like to. I'm just moving around my negative charge or my lone pair and shifting the double bonds as appropriate to make sure no carbons end up with more than an octet. Okay, and I guess really I should have my lone pair drawn up here. That's where the arrow's coming from. Okay, so 5 versus 3. The one with more resonance structures is more stable. Okay, back to the paper. Give me a sec. Okay, this one is also resonance wants to know which one is a stronger acid. We need to think about which one is the more stable conjugate base. So here's my conjugate base on the right. This one has a kind of a special resonance structure that's enabled by the fact that these are like on opposite ends of the ring. They're not closer to each other like they are here. This is called a para arrangement. We'll learn about this later. I can move this down to make a double bond, which is going to cause this one. Then this double bond is going to have to shift between these two carbons. And this double bond is going to pop out to make a double bond here. And then this double bond is going to pop up to this oxygen. So I get this special sort of quinone-like resonance form that looks like this, or resonance structure, right? I had a new double bond here, then this came down and made a new double bond to this carbon, and then that has just a single bond to my oxygen with my negative charge. Okay, well, you guys can't even see what I'm drawing. This is my new resonance structure, right? This became a double bond, this double bond moved here, this double bond moved between these two carbons, and then this double bond went up onto the oxygen to become a lone pair. So I have another good resonance structure that stabilizes my conjugate base by a lot. So this is my stronger acid. You can't draw a resonance structure like that with the guy on the left. Okay, if you try to draw the conjugate base of this, you can't move it. You can't move that lone pair in the right way. Because if I try to move this down, I make my double bond here. This becomes a double bond here. This one I can't swing it down this way because then this carbon ends up with too many this carbon will end up with too many bonds to it. Okay, so there's not a resonance structure that you can draw like this. You can't draw it with this orientation. Okay, so this one's resonance stabilized better, so it's a stronger acid. Okay, don't forget I have a review session on Monday. If you're watching this after Monday, I hope that you went to the review session. You can still come meet with me on Tuesday. If you email me a time, I'm free pretty much all day on Tuesday because we don't have lab. And otherwise, good luck on the exam. Send me an email if you have a question. But if it's too late, if this is like midnight on Tuesday night, good luck. Get some sleep. Don't forget to get some sleep. Eat breakfast. Drink some water. Get some sugar in your system. Okay, I'm going to stop the video now. I'll see you guys later.